So if you understand what they mean, you can write your indices in an intelligent fashion. Okay. From this, but I know what x2 is. There it is. So this is known, so I should take it to the side with all the knowns. So that means I've got b1 minus a1 to x2. I'm not going to substitute in because it doesn't add anything to substitute in. But that's equal to a11 x1. But that means I could just divide by a11 as long as it's not 0. So again, notice this had to be not 0, and this has to be not 0. But do I have any requirement on a12 being anything? No, who cares? So this is why we worry about the main diagonal. This is where your pivots are going to be, right? When we get down here, what we care about is that this main diagonal is not 0, because then what I can do is just solve backwards, right? Then I know what x1 is. If I know that, I can go the next level, right? If there was another level above this, I would now have 2 that I could substitute in, and I'd now have 1 unknown. So I'm kind of starting at the bottom and working my way back upwards. So as opposed to starting at the top and working my way down, which you kind of think of as forward, this one is backwards. And all I'm doing is I'm solving for 1, and then I'm substituting it back in, simplifying the equation, and going to the next one. So I'm working backwards, and I'm substituting the values as I go. So this is called back substitution. There you go. So if you have a triangular matrix, this is kind of the classical form of triangular matrices where they're up like this, I can do what's called back substitution. It's a really simple process if you think about it. The idea of the process is very simple. The execution of the process is actually pretty simple as well if you walk through it that's going on. I'm going to have to deal with everything in the row. I'm going to substitute in my values from my last ones. So that'll be 1 multiplied per each, and I have to add them together, take them to the other side. Okay, 1 more. But that's still proportional to the number of elements in the row, with 1 thing left over, which I'll do a division on. Okay. So it takes me up to n things per row. I got n rows. So basically, you're looking at an n squared algorithm. So this is where the meat of your work is doing on anything else as well that's going on. As long as you can get to that n squared. If you're n cubed, this becomes unimportant. Now I can tune this and all kinds of other stuff. So this is what we call back substitution. So if I can get things into this form, at that point I just go, I know how to solve it, pull out the standard algorithm. And we typically write this algorithm very generically and just let it solve. Because this is one of our fundamental building blocks. Make sense? All right. Let me ask you a question then. What if A, instead of being an upper triangular, was a lower triangular? What would I do now? Invert it. So how do I invert it? I mean, because, you know, if I do something, I mean, I could transpose this, right? But to transpose this, I'm going to get B transpose equals X transpose A transpose. And now A transpose is the right shape, but everything just got all ugly. Right? It's no longer exactly the same form. Now, I could invert the order inside my X and invert the order inside my B that's going on, and I could find a permutation that'll flip everything around. Make sure the last equation goes to the first, or I have to flip all these. Right? And I make sure the last of these goes first, and it'll flip it to the upper form. But now I have to invert all my equations, both on X and on B. That adds a bunch of extra complexity and memory swapping and all kinds of other stuff. So I could do that. So I don't just want to do the straightforward transpose, right? Because that's kind of ugly as it's going on. I could do this kind of inversion thing, but I'd still at that point be flipping these matrices. That's a lot of operations. I mean, think to flip A, right? I in essence have to move every one of n squared, right? N by n. Everyone. So it's n squared just to flip that. It costs me just as much to set up that equation as it will to solve it. That's almost insane. Okay? So the question is, can I develop something analogous to that that would just be easier to write as a simple piece of code that can operate on this without having to manipulate the data so it goes quicker? So what would I do in that case? How could I solve such a BC? Silence doesn't scare me. Everybody watching videos doesn't care, and I can snip it if I need. Right? I want you to think of it. So what did I do to solve it? Right? Did it satisfy you the way that I solved? Okay, so take a look not just at, oh, here's the answer. Right? Answers are cheap. You can look them up on the internet. You can look them up in the book, all kinds of stuff like that. The idea of how I got there is actually the more useful in this that's going on. What did I do to go from a big problem to solving that big problem generically? I took an intermediate step of solving a small case. And then I showed how I could generalize that small case. That what I did in that small case was true in general for everything else. Yeah, maybe you have to do a little more substitution, but who cares? The idea is the same. This is a fundamental one of our solving techniques. And I submit to you one of the first things you should do when you're trying to solve a problem is A, draw a picture, and B, see if you can write a simple example. And if you can solve that simple example, you look at how do you solve that simple example, and then try to systematize it. And then see where can it break, and you add kind of defenses around it. You'll get 90% of the algorithms just by that method. I picked 90 out of the blue, but an awful lot of them, right? So truth be told, I haven't checked to see is it really 90, but a really huge number of them you're going to be able to get by doing that, because that's how we got them in the first place. So what can I do?
Just doing the same thing with that, but starting from the top instead of the bottom.
Exactly. So I'll just start at the top, because that's where I want to go. Except this time, I start with which row? The top row. So I just have B1 is equal to A11 X1. Again, nicely matching the coefficients. It sounds tedious and it's obvious in this case, but trust me, when you write your code and you're dealing with all kinds of funky stuff, you're going to want to make sure you match it. Most errors are either off by 1 or mismatched coefficients. If we could eliminate those two errors, you'd probably destroy 90% of the errors. There we go, picking 90% again, right? It's kind of funny how often we pick 90% as a thing. That's, sorry. Bad joke, but also social commentary on where it goes on. But you really will get a large number of the errors knocked out if you handle those. And so my general statement is, make it easy for you to solve the common errors. And your code will be less buggy and you'll be faster. Right, so we end up with B1 over A11 equals X1. I substitute it back in, remove this one, I take it to the other side, solve for the next one. It goes in, it'll look very similar, except it's just going in the opposite direction. Well, this one is kind of proceeding top to bottom and left to right. So that's kind of the way we typically think. So this is forward and we're substituting in, so this is forward substitution. We almost always give you both algorithms. And the reason is it just lets you avoid the other things. And we can just write these and tune it so it's very efficient in your memory system. That's the other thing that really matters here is taking advantage of cache. If if you take advantage of your cache system so that you get a lot of memory hits when you're doing this, it will increase. Cache typically is about 2 orders of magnitude that's going on. And the reason that works out is order of magnitude is power of 10. So if you think about it, to access a register or an on-chip cache, it's going to be on the order of nanoseconds or fractions of a nanosecond. Whereas if you're going to go out to main memory, it's going to be on the orders of 50 to 100 or more nanoseconds. So that's your 2 orders of magnitude. It's just in the access time. That's just basically how the thing is physically built. It takes you about 100 times longer to go to RAM than it does to go to a register on the chip. So we want to stay on chip as much as possible to keep the speed up. And so it's faster to tune these. So this is why once you learn the algorithms, you learn where it's good, you learn where it's bad. Right? What's going to become important is not to use your own code. This will seem really strange, but because I'm going to be telling you to write your own code, try it, test it, and then I'm going to tell you not to use it. The reason why you don't want to use it is if there is an established, already out there library that has been tuned for your platform. Somebody who has as much knowledge as you do at that point spent the time to look and say, how do I tune it for the cache for this particular system? So they've done a lot of tuning you just don't have the time to do. You could do that, but it's already been done, so why bother? You want to write your own algorithm because you need to understand where the problems are. You need to know where can you use it, where will it fall apart, all the rest of this kind of stuff. But once that's done, you now understand it. If you get hired to write one efficiently or tune one for a particular platform, for those compiler options for this particular system, then great, you know how to do that, you can go ahead and do that. Otherwise, use somebody else's labor. If you never wrote it, you wouldn't understand it, so you couldn't use it well. So that's why I think it's important to write the code and then don't use it. Use a good library. The good libraries are like, there's a whole bunch of these. The BLAS, the basic linear algebra subroutines that's going on. And there's different levels of this, up through level 3. And they start at the basic functions, so like your substitution, forward and back substitution, and multiplies and all that kind of stuff, working their way up to fancier algorithms that's going on. And you'll also find there's like LAPACK, linear algebra package, right? And there's IcePack, right? Eigenvalue subroutine packages. Right? So there's tons of these different ones that are out there. There's LinPack, right? That's out there that also deals with linear equations solutions. So there's all these packages. A good source for all these is NetLib. So if you go to netlib.org, they've got these packages available for almost every major platform that's out there that's going on, and you can download them. So once you get them, then show that you're in the know. Go to NetLib, get the appropriate ones, download them, install them on your machine, and use good packages. NVIDIA has these for theirs, right? This is actually why I originally went with NVIDIA that was going on, because their competition didn't support all of these. And NVIDIA supported an awful lot of it. They still don't support all of it, but they supported more of it than any of their competition, which allowed access to well-written routines. These routines have been worked on since the 60s and 70s that's going on. So you just have, literally some of the best minds working on these, tuning these algorithms, for the last half century. So it's gonna be something you write this weekend. Although the basic things will still carry through. We feel good? That's going on? All right, so now we've got forward and back substitution. If I have a triangular matrix, whether it's upper triangular or lower triangular, boom, I'm done. Right? What happens if it was really nice and, instead of being triangular, it's just diagonal? Right? Well, then there's no substitution necessary, right? Each one, my goodness, it's parallel. Now there's a second thing that it gives you besides parallel. So it's stupid fast because it's parallel. They can all be done independently. All right, which means I can throw them out on a parallel processor very fast. There's a second thing that's going on here. A22 can't be 0. But what happens if A22 is really small? 1 over something small is really big. Right? So this can be huge. What if there were some errors in B2? When I measured it, there were some errors. And then I'm dividing by something small, which is multiplied by something big. What happens to the errors? They become big. So those big errors that are coming in could actually, since this now comes in straight linear here, it's actually being multiplied by something. If A12 is not small, if it's fairly big, right? So if A12 is on the size of A11, the errors from here will be at least as big, if not bigger, than my B1. So the errors from here can swamp this term. But that is now being divided by A11. If it's small, guess what happens? The errors of this will be big errors made bigger. So what can happen as I'm working up is these errors can build. And again, a lot of different terms coming in. If each one of those have errors, those errors can get bigger and bigger and bigger, snowballing, so that at the end, you think you're going to get anything good? No. Right? That's how it fails. You can actually correctly pick the coefficients inside of A so that the errors build really, really nastily. But you can already see the idea, right? I want these to be small and I want these to be big. That's going on. This is why we typically like to deal with matrices we call diagonally dominant. That means the diagonal terms are the biggest. Because if these are small, the division problem carries up. And if the off diagonals are large, they're bringing in a lot of error from the previous stages. So what you really want is the off diagonal element small and the diagonal elements big. Well, a diagonal matrix clearly does that because the offs are 0 and the diagonal is non-zero, so it's awesome and they're all independent. No error builds. So if you had a diagonal matrix, the errors won't build. If you've got something else, and that something else has large off-diagonal terms, what we can call the cross couplings, because it goes from one connection to the other. This is part of the other reason for the setup. If those become big, you're going to get ugly errors, just the reality. So we want those to be, if possible, as small as can be. And that becomes important for our error tolerance when we're going on and solving. All right, make sense? Okay, so now how do we get to this form? It shouldn't surprise you if I told you this is where most methods spend most of their time. Actually, we have a huge number of algorithms just to figure out how to solve this problem. How do we reduce something to triangular form? Because once I got it in triangular form, I have a solution. Right? And that solution method I know how to handle. In the lectures, I deal with household and QR. So I'm just going to give you a real brief overview of some different techniques that are out there, and then we can work on them. One of the first ones, right, so we have, if I have B equals AX, what if I could rewrite A as a lower triangular matrix times an upper triangular matrix? Right? If I could say A equals LU, and I can figure out, for any A, I could figure out L and U. Then I would just have this problem, B equals LU times X. Now, all I have to do is call this, let me call this Z. So what I have is B equals LZ. And then Z is equal to UX. So this is B equals L lower matrix times Z. But a lower matrix, I can just solve this to get Z by using forward substitution. That gives me Z. I then take that Z, stick it in here. This is an upper, so now I can do backward substitution to get X. So if I can do this factorization problem, I can just go in and solve this way. Now that being said, this in theory shows that it can be done. Don't do it this way. It turns out you can do this first step for free. So it's just a waste of time. And we'll talk about how to do it for free on the area. But I can do it as part of the factorization. That's really what the trick comes down to. And that just lets me skip a step. And if you can skip a step, you know, you pay for it as you're going through, but you end up paying less because you just bundled it. But this also underscores an important idea. There's a way I can prove to you that this method works, but the way I prove it to you is almost never the way you should actually solve it. Because there are two completely different beasts mathematically. How can I show that it works, the idea is a good idea, and then what's the good way to actually solve it? The tricks necessary to make a good solution technique so it's fast are very different from what makes it easy to prove that it's true. Okay. So this one's just kind of a proof that it's true. Okay, so now we get into, I would like to be able to do this factorization, L times U. This turns out to be what we call Gaussian elimination. Gaussian elimination. I'm just going to abbreviate. So this is another one of those areas where it just turns out that Gauss punked us all by several centuries, right? Because it turns out that Gaussian elimination is one of the fastest techniques that's out there. And there's some variants, Gauss-Seidel and all kinds of stuff like this that goes on. But it turns out, you know, in yet another area, even before matrices existed, Gauss came up with a way to solve them that turns out to be actually pretty decent. Now the danger with Gaussian elimination actually comes in not as much in Gaussian elimination, which is fast, and you can do some nice stuff. It turns out the errors build when it goes in, and then the errors build again. So you can end up with some really ugly errors if it's wrong. So almost all the solution techniques for this involve making sure that the errors don't build here. What we want to do on the first one, when it's coming up here, it's working on the order of the equations. We'd like to make sure that those main diagonal elements are big. So we have what we call partial pivoting and full pivoting. This just kind of gives you the overview. What's going to happen, partial pivoting is going to try to look in each column, find the biggest element, and move that to the pivot. So that column-wise, it's just going to pick the biggest pivot in a column, move that to the diagonal, and it'll shuffle the equations so that I get the biggest diagonal or the biggest entry in any column into that diagonal area. That's partial pivoting, right? So that's going to improve things by making the diagonal bigger, which will therefore avoid that problem of error building. Now, it's theoretically possible if my matrix looked like this, 1, 2, 5, 10, that's going on. It would really be nice to have that 10 up there. Right? Partial pivoting is going to choose between the 1 and the 2. And then it'll choose between the 5 and the 10. And it'll get the 2 here, but then your 10 will be locked. So your biggest element in picking this one, I'm going to constrain that one to be the worst. Full pivoting looks at the entire thing and pulls the biggest entry up to the top. Because remember, I can shuffle X and I can shuffle B. It's just a shuffle. So I can, if I do full pivoting, I'm pivoting the rows and the columns. It just means shuffling them so that I force the 10 to come up. So that will give me my biggest entry on the diagonal. Remember, the bigger entries on the diagonal means less error building. So I can still force partial pivoting to have problems. Full pivoting just looks everywhere. That's all it's doing. They will look tremendously more complicated because what you have to do is you're searching through things to find the biggest ones. And at each step I find the biggest one, I move it up, right? I'll then have to look through like everything else for the next one, right? So it's going to get smaller and smaller, but I'm still going to have to check through a big submatrix to find the next biggest, and I have to shuffle them, and I have to keep track of the order of the shuffling. Right? So this is just part of that whole process that goes on. but that's really where the separation goes on. That being said, I think it becomes ugly. So I'm going to leave it for the algorithms in the book to deal with. Hopefully if you understand the idea that it's just shuffling to just get good elements, other than that, the method doesn't change. So what did Gauss do when he was going on to these? I'm going to do my same trick that I did last time. I'm going to write a small subproblem, and then we're just going to solve it. So imagine I have B1, B2 is equal to A11, A12, A21, A22. And I've got my X1, X2. Now I'm trying to solve for X. I know the A's and the B's. That's going on. Now, what I want to do is I want to get a 0 here. So I'm trying to target that. Now, the way Gauss does it, he's going to develop the L for free. That's going on. He's going to make a matrix L that's going to solve this. Okay. Do we need to take a break? Is everybody a little tired? We need a stretch? Yes? Okay, let's take a break. I'll come back to this in a sec, as if I didn't go anywhere.